Hello, physics students. Welcome to Chapter 7 lecture. Chapter 7 is about Newton's third law, which is like the action-reaction pairs for forces. We always kind of have the saying, every action has an equal and opposite reaction, but if we tighten that phrase up a bit, it's kind of more like every force has a reaction force. There's action-reaction pairs of forces. And it's interesting how that's going to work. So, take this hammer and nail, for instance. The hammer is obviously going to produce a force on the nail. But what is not intuitive but true, and maybe the more we think about it, the more it will become intuitive to us, is that the nail also produces a force on the hammer that is equal to the force the hammer is producing on the nail. That's kind of anti-intuitive because obviously the nail is going to be affected so much more than the hammer is by this interaction. And the reason for that is not because the forces are different, but because the masses are different. So they each produce a force on each other that is the same magnitude force, although opposite in direction or opposite in sign. The nail is affected much more than the hammer because the mass of the hammer is more. So F equals ma means if F is the same, but m is very different, then the resulting acceleration is going to be very different. So if the mass of the hammer is bigger, the acceleration of the hammer is going to be smaller. The force is going to cause a smaller acceleration on the hammer than the nail. If it has a smaller mass, it's going to cause a larger acceleration on that nail. I hope that makes sense to you. Let's keep going. So here's a preview. All forces are interactions in which objects exert forces on each other. If A pushes on B, then B pushes back on A. These two forces form an action-reaction pair of forces. One can't exist without the other. All right, I'm going to go ahead and tell you kind of a physics parable. It's a classic one. So a man has a horse, and the horse is attached to a cart. And the man, says, "Giddy up, horse, let's go." And in this parable, horses can talk. So the horse turns back to the man and says, "Master, you need to understand physics here. If I pull on that cart, it's going to pull back on me with the same amount of force. And so there's no way we can go anywhere because of Newton's third law." And the man, because he did not take physics like you are taking, he probably took anatomy or something. Just kidding. He was kind of sitting there dumbfounded. All right, so your task is to help this man. Why is that horse wrong and just trying to get out of work? Why is it Newton's third law not going to actually support what the horse is saying? By the end of this chapter, we need to be able to go revisit that parable and answer the horse's objection. If A pushes on B, B pushes back on A, these two forces form an action-reaction pair of forces. One can't exist without the other. What is an interaction diagram? We often analyze a problem by defining a system, the objects of interest, and the larger environment that acts on the system. An interaction diagram is a key visual tool for identifying action-reaction forces of interaction inside the system and external forces from agents in the environment. So just like we've been doing in kinematics and in dynamics, so the newest thing we've done in Chapter 6 and even Chapter 5 was a free body diagram with a dot and the force arrows and all that kind of stuff. This new thing we're going to do here is called an interaction diagram. All right, we'll get more into that as we go. How do we model ropes and pulleys? That's another question for the chapter. A common way that two objects interact is to be connected via a rope or cable or string. Pulleys change the direction of the tension forces. We will often model ropes and strings as massless, pulleys as massless and frictionless. The object's accelerations are constrained to have the same magnitude. In other words, whatever the acceleration of B is, because they are attached to one another, that A will have the exact same acceleration, although it perhaps could be a different sign. All right, so in order to keep things simple, the cable or whatever it is connecting the two, we often are going to think of that as massless, or at least negligible mass, so that it keeps this more simple. And the pulley itself, we're also going to think of that as massless, so that the rotational inertia of this pulley we will think of as negligible. And also frictionless, so that the friction of the pulley itself won't be taken into account either, just to keep things simple for a good long while. We may end up dealing with mass and friction and all that of this system, but at first we're not going to consider those things. What is Newton's third law? Newton's third law governs interactions. Every force is a member of an action-reaction pair. The two members of a pair act on different objects. The two members of a pair are equal in magnitude but opposite in direction. Okay, that's a good exposition of Newton's third law. How is Newton's third law used? The dynamics problem-solving strategy of Chapter 6 is still our primary tool. Draw a free body diagram for each object. So this is what we're going to do. So now we have two objects instead of just one. Each object is represented by a dot, and we have these forces like we have had before, but now we're trying to link, if there's a force here on this object that is connected to, that is an action-reaction pair with a force on this object, a lot of times we may draw a little dashed line or dashed curve between them just to communicate that, so that we can remember that because it might make some of the math more simple. Okay. Why is Newton's third law important? We started our study of dynamics with only the first two of Newton's laws in order to practice identifying and using forces. But objects in the real world don't exist in isolation, they interact with each other. Newton's third law gives us a much more complete view of mechanics. The third law is also an essential tool in the practice and application of physics problems to problems in engineering and technology. Okay. Here is some reading questions. Let's see if we can know these without reading. If we can't, it'll tell us what we don't know. Two forces for which Newton's third law applies are, I bet you already know just from the introduction, an action-reaction pair. What kind of a diagram is that? Again, you probably know this from the introduction. We call that an interaction diagram. The propulsion force on a car is due to what? In other words, what makes the car go forward? The car engine is right in an overall sense, but not in a physics free body diagram sense. The engine makes the wheels turn. That's an internal force of the car. But what actually propels the car itself forward, including propelling the engine itself forward, is actually the fact that the wheels turn and it produces a static friction with the concrete or asphalt or whatever it is. So the car's tires produce a force on the concrete, which is kind of like on the earth basically, and then the earth pushes back with an equal and opposite force on the car that then propels the car forward. See, the car can only go forward by something outside of itself, which is going to be what the earth does. We say the ground or the asphalt to the car. It's interesting to think about it that way. Is the tension in rope 2 greater than, less than, or equal to the tension in rope 1? This is a very interesting thing to think about it. I'm going to let you think for a while. You might want to pause it and think about it. You might think the tension here in this rope, if he's pulling with 100 newtons, would only be 100 newtons. Whereas the tension of this rope, because he's pulling with 100 newtons and she's pulling with 100 newtons, is 200 newtons. But what we forget is that the rope, he's pulling on that rope with 100 newtons, which means the rope is pulling on that wall with 100 newtons, which because of Newton's third law means that that wall is also pulling back on that rope with the exact same force, just like in this second diagram. So the wall basically is the girl, taking the role of the girl here in the second diagram for the first diagram. So the forces in the rope in both diagrams are equal. An acceleration constraint says that in some circumstances, you might be able to get this from the introduction. Read the choices and think about it. It is choice C. The magnitude of the accelerations of two objects have to be equal. That's in certain situations because of the connection between the two objects with a rope or a cable or maybe something even more than that. That the objects have to have the same acceleration. At least in magnitude, their accelerations have the same magnitude, although maybe not the same direction. Alright, so interacting objects. When a hammer hits a nail, it exerts a forward force on the nail. At the same time, the nail exerts a backward force on the hammer. Here's a good little thing to think about. If you don't believe it, if it's hard to believe, imagine hitting the nail with a glass hammer. Obviously, the nail is doing something to that hammer because that glass hammer would shatter. It's the force of the nail on the hammer that would cause the glass to shatter. When a bat hits a ball, the ball exerts a force on the bat, just like the bat exerts the force on the ball. When you pull someone with a rope in tug of war, that person pulls back on you. When your chair pushes up on you, the normal force, you push down on the chair. Every force comes in a pair called action-reaction pairs. These forces occur simultaneously, and we cannot say which is the action and which is the reaction. If object A exerts a force on object B, then object B exerts a force on object A. The pair of forces as shown is called an action-reaction pair. So we call this force the force of B on A, and we call this force the force of A on B. And together they form an action-reaction pair, equal magnitude, opposite in direction. Chapters 5 and 6 considered forces acting on a single object modeled as a particle. The figure shows a diagram representing single particle dynamics. You have an isolated object. Forces, outside forces, are acting on that object, just like we've been saying back in chapter 6. We can use Newton's second law, which is F equals ma, or if you rearrange it, A equals F over m, to determine the particle's acceleration. In this chapter, we extend the particle model to include two or more objects that interact. This figure shows three objects interacting via action-reaction pairs of forces. The forces can be given labels such as Fa on B and Fb on A, and so on and so forth. Each line here represents an interaction via an action-reaction pair of forces. So this particular line actually is going to represent an interaction and an action-reaction pair of forces. That's a little bit confusing. For example, object A is the hammer, object B is the nail, object C is the earth. The earth interacts with both the hammer and the nail via gravity. Practically, the earth remains at rest while the hammer and the nail move. Define the system as those objects whose motion we want to analyze. Define the environment as objects external to the system. So if we just want to analyze the motion of the hammer and the nail, we would actually define the system, an open system. I haven't even told you what an open and closed system are. An open system is a system in which there are forces from outside the system happening that are affecting things in the system. A closed system is a system in which there are no outside forces affecting the system. So you have a system right here, an open system around A and B. So that A and B are in the system, and C, which is the Earth, is outside the system. So C would be a part of the environment, quote unquote. Figure shows a new kind of diagram, an interaction diagram. The objects of a system are in a box. Interactions are represented by lines connecting the objects. Interactions with objects in the environment are called external forces. So these are internal forces, internal reactions to the system. And these here, because they go outside of the box, are called external forces. Here are some very good things to keep in mind. Represent each object as a circle with a name and a label. Place each in the correct position relative to the other objects. This is interesting right here, something to keep in mind. The surface of the Earth, you may label that S, which has contact forces like friction and normal force. And the entire Earth, you might label that EE for entire Earth, only has a long-range force, should be considered separate objects. Should be considered separate objects. In other words, the surface of the Earth versus the entire Earth, you might put those as two separate circles in your interaction diagram. That's necessary because the entire Earth is going to cause gravity on the objects that we're trying to analyze, whereas just the surface of the Earth is producing a normal force and a frictional force. So you want to separate those out, and you have to do that in these interaction diagrams. Draw one connecting line between relevant circles to represent each interaction. Every interaction line connects two and only two objects. So I think it's saying that every line, back in this diagram right here, every line represents a pair of forces. Like this line would be like the force of A on B and B on A in that one line. This would be the force of A on C and the force of C on A in that one line. I think that's what it's saying, but I'm not 100% sure yet. This part always confuses me of what they're saying about that. It'll be clarified in a little bit. A surface can have two interactions. A surface can have two interactions. So you may have to draw two lines to show that. So friction would be one interaction, and normal force would be a whole different interaction, although it's between the same two things. Okay? Analyze interacting objects. Identify the objects of interest, draw and label a box enclosing them. This completes the interaction diagram. Draw a free body diagram for each object in the system after you have done the interaction diagram. Include only the forces acting on each object, not forces exerted by the object. So again, in your free body diagram, that's something we already knew. When you draw the dot representing the object, you don't put any forces that thing is doing on that dot. You only put the forces that are being done to that object on that dot. Every interaction line crossing the system boundary is one external force acting on an object. The usual symbols such as N and T, like normal force and tension, can be used. Every interaction line with the system represents an action-reaction pair of forces. Every interaction line represents a pair of forces. So it is what I said earlier. There is one force vector on each of the objects, and these forces point in opposite directions. So we use those labels we talked about earlier. Connect the two action-reaction forces, which must be on different free body diagrams, with a dashed line. Pushing a crate. Figure 7.4 shows a person pushing a large crate across a rough surface. Identify all interactions and show them on an interaction diagram. Then draw the free body diagrams of the person and the crate. Alright, so if I were trying to draw an interaction diagram, I would have, let's let this be the man, the person. Let's let this be the crate. Then we got to have the earth. So this is the system that I care about analyzing the motion of. But then outside that system, we have the surface of the earth causing friction and normal force. We also have the entire earth causing gravity. So what do we have? We have an interaction right here. That's a push of this single line represents the interaction between the man and the crate. So it represents that there's a push by the person on the crate, and also a reaction, a push of the crate on the person. Okay, the surface of the earth has a normal force on the person, just as the person has a downward force on the surface of the earth. There's also friction, so I'm having to draw two lines to represent that. There's static friction between the person on the surface of the earth and the surface of the earth pushing back on that person. That's actually what propels the person forward. Likewise, there is a normal force and a downward pushing force from the surface of the earth and the crate, and friction between the surface of the earth and the crate. Same way. And then here, there's also gravity between the earth and the person and the earth, and gravity between the crate and the earth. And it's supposed to be one line, I'm sorry. Didn't really do that too well. And the earth and the crate. Now we can do a free body diagram for just the things that we care about analyzing the forces on. So I'm going to do a free body diagram for the person. I'm going to do a free body diagram for the crate. So what do we have? What all do we have acting on this person? We have a pushing force of the crate. I kind of trapped myself in a corner, didn't I? The pushing force of the crate on the person. We have the normal force of the surface of the earth on the person. We have a frictional force, actually, that is pushing the person forward. It is the frictional force it's this frictional force right here that the man's tennis shoe or whatever it is causing a static friction on the earth, and then the earth is pushing back with an equal force to that static friction on the man, and that is what is actually pushing him forward. So that's just going to be the force of the surface of the earth on the man. We also have gravity. Yeah, so we could do that. Person. Raise this up a little bit. Crate. Alright, so how many forces should we have? We should have 1, 2, 3, 4. And how many do we have? We have 4. What about the crate? We have the pushing force of the person on the crate. We have the normal force of the surface of the earth on the crate. We have the gravitational force of the entire earth on the crate. We have friction. And so I could say the friction, which is the surface on the crate, but maybe you could just do friction like we've been doing and just put static friction right here, static friction right here, although they're two different static frictions, so I'm going to have to differentiate them somehow. This is static friction for the person, whereas this is the static friction for the crate. Alright, hopefully that wasn't too confusing. Now, we also want to link the action-reaction pairs. We might think that the normal force and the gravitational force are action-reaction pairs, but that's not actually true. The normal force would be an action-reaction pair with the surface of the earth. It's pushing down on the surface of the earth with the same amount of force that the surface of the earth is pushing back on that. The gravitational force is a long-range force, not a contact force. See, normal force is a contact force. The gravitational force reaction pair would actually be the gravity of the person back on the earth, which is, not going to be doing anything. It's completely negligible, but it's there. So these are not action-reaction pairs, although they mostly act like it. They especially when you're on a flat surface, the normal force and the gravitational force are equal in magnitude when you're on a flat surface, but they're not equal in magnitude when you're on a slanted surface. So they're not action-reaction pairs. Now, what are action-reaction pairs are the force of, let me do a different color. Let me do green with a very small line. That is an action-reaction pair. The force of the crate on the person and the force of the person on the crate are an action-reaction pair. Okay. The force of static friction, this is the static friction of the surface on the person. Its action-reaction pair is not in this diagram. It is outside. It's outside of the diagram. It's right here. It's right here. So it doesn't have an action-reaction pair inside this diagram. Same with this one, which is the same reason the normal force and the gravitational force don't have an action-reaction pair inside the diagram, because they're actually outside of the diagram. They're here out in the environment is where their action-reaction pair exists. So the only action-reaction pair that truly exists in this diagram is this action-reaction pair of the crate on the person and the person on the crate, which makes sense because they're the only two things in the system. There's one more little detail I need to put. If the force of gravity here and the force of gravity here are not the same because their masses aren't the same, I need to distinguish things. I can't let the same symbol represent two different quantities. So I need to put an extra subscript here. This is the force of gravity for the person. And this is the force of gravity for the crate. So you have to use some subscripts to distinguish these things sometimes. All right, let's see what the book says. Here's the interaction diagram, which is what we have as well. Push force between the person and the crate. Normal force between the surface and the person. Same with the crate. The friction force between the surface and the person. Same with the crate. And the gravitational force between the person and the entire Earth. Same with the crate. And we then get to this this free body diagram, which is exactly what we said, that you got the normal force, the force of the crate on the person, force of gravity on the person, the force of friction on the person, and the same stuff over here similarly. And then we have the line, the little curve drawn here that connects those two as an action-reaction pair, which makes the math for those easier when we get to the equations, because we know those have to have the same magnitude. So it's one less variable to have to find. All right, let's stop right there, and we'll call that part 1 for chapter 7, and then we'll continue on with part 2.